So it dawns on me that I'm not following along in R with all this. Let me show you some matrices in R while we go along, vectors and stuff real quick, okay? Okay. So we have our data. This is from our EPSY 905 package. You see our data set. This in R has different ways of storing data. We're going to get to that in just a moment. This is our data set. It has an ID character on here, so I end up taking off. A data frame in R looks like a matrix, right? It's very rigid if you think about its structure. It has a set of columns that represent variables. It has a set of rows, in our case, that represents observations. And if a person somehow didn't give you all the data, like if I only had one person, like the first person didn't give me SAT verbal, it would have a NA for missing data in the spot of where the data happened to be so that the shape of it still holds, right? So that's kind of giving you the first step. The data frame, though, is different from a matrix. So if I go and take each part of the data frame, so data 01, if I type data 01, you hit the $sign, and let's say like take SAT verbal. What you see that R gives me now is no longer a rectangular array of numbers, as much as it's just this listing of 1,000 numbers in a row. Right? And the fact that the 1,000 spans this size is only because my screen is the size it was. You don't need to see my Google Drive. And so if I resize my screen, it's literally what this is. So when you just take one of the variables out of the data frame in R, it's no longer part of a matrix in R language. It's what R is calling an atomic vector. It's like the very base, the building blocks of what exists in R is this, right? So this is, if I were to call this R at atomic, like that, R atomic, when you go over to your environment, you'll see it just shows up down here under values rather than up here with the data. And that's because the atomic vector in R is something you can't do matrix algebra on. That's the big distinction with it. So does that seem a little weird? Data frames, you might be able to do matrix algebra on. Depends on if you're containing characters or not in them. Data frames can each variable in a data frame can be a different format. It can be character or logical or numeric or integer. But you can't add characters together. So that's the main thing, right? Atomic vectors in R are just like strings of numbers. There's one dimension to them. So if I wanted the fourth observations SAT verbal, I could do R atomic, and in brackets put number 4, and I get the fourth number in the list, 560. Are they ordered by size? They are not ordered by size. They are ordered by how they appear in the data frame itself. So if I go back to my data, right here, oops. It's however it got into the data frame in its first place. So person 4 has a value of 560, and how that shows up is how the data were imported, either in your Excel file or whatever way they were brought into R in the first place. Juhi.
So this is just a way of explanation how data points are distributed in space.
That's right. Matrices can be thought of as visual representation in space. But in R, they're now how they're stored in the computer, right? So in general, you can think of matrices as having a geometric component to them. Although the computer itself lacks that geometry, it's more just a filing system. So when we get back to R, the next thing to do, whenever you use the function, sometimes you've seen me, speaking of atomic vectors, you may have seen the concatenate function. So if I created the vector, if I call this R atomic 2, and I say it's C of 1, 2, 3, that C function right here takes the numbers 1, 2, and 3 and puts them in 3 elements of this atomic vector. Right? So this is just a vector right here. Oops, shoot. An element of vector is the number that shows up in the numbers in the actual numbers. So here you see 1, 2, and 3. Each one of those is a separate element.
And 1, 2, and 3 is the position of that element?
Well, no, it's just the number that's actually there. Here, how about I do this? Oh, nope. Dang it. 1, 20, and 3. So here, in the atomic vector, if I wanted the second element, that's the second position, it would give me the number 20. Right? So here, in that vector, in that list of numbers, an element is the index value where that number shows up in serial. And it can be stored in any order, just that's the number from 1 to the end of that. So you with me so far? It's a little weird. This is the thing that threw me off from R for years. Let me tell you this. Because some packages want you to do things with data frames. Some packages want you to do things with matrices, which are different from data frames, and I'll describe those in just a moment. And some packages want you to do things with atomic vectors. And the key is, not all of those can do the same things. Like this class with matrix algebra talks about the matrices and what you can do with them. Cool, right? So matrices in R can do what matrix algebra wants them to do. Sometimes data frame can. Sometimes, not all of them. But matrices absolutely can. Atomic vectors cannot. So let me show you what a matrix is in R before I get into the differences between the two. If I took the two atomic vectors, this SAT verbal and SAT math, and I put them in the cbind function. What cbind stand for is column bind. It takes them as column vectors and puts them together in a brand new matrix that has as many elements as you tell it to put in here. Right? My matrix X, if I were to type class of X, it will tell me it's a matrix. Whereas if I type class of R atomic, it tells me it's an integer. And class of data 01 tells me it's a data frame. These are all different types of ways that R stores numbers. And the key distinction is when you're doing matrix algebra or matrix algebra type operations, typically you want them to be in this matrix format. It seems very subtle because matrices, data frames look like matrices. But matrix is really the one you want. The reality of it is a matrix in R can only contain information that is of the same type. So if all the variables in the matrix are numeric, the matrix is numeric. You can't add a character variable to a numeric matrix. Let me show you. Can I show you this? If I were to go over here and type as.character turns a numeric variable into a character if it can. And let's imagine I give it data 01 star ID. So now instead of having a numeric ID, I have this character ID. It's the numbers in quotes. It's going to tell me it can't, oh, I guess it can do that, never mind. Oh, so, but see what happened. It can do that, but look what it did to me. You see my matrix? It's a bunch of characters. Have you ever added the character 2 to the character A? It doesn't work, right? So you can't do numeric operations on characters. So this is where I wish it would have warned me. I thought it was going to do that. Anyway, matrices all have to have all the same type of information in them. And typically, for us to do matrix algebra, it all has to be numeric information. Right? Some type of number that goes with it. With me? Kind of a weird distinction. This is why in GLHT, did you see if in the syntax I had, let me see if I can pull some of that example syntax up. I forgot to mention I put my predictions up for this year's tournament. I don't know if you've seen them on my website. Here, I'll grab my example file here real quick for GLHT. But you'll see right here, tournament predictions. Or I'll quickly go in there. It's much more interesting. Who's going to win this year? Arizona? No. Arizona has had about a 1% chance in my model.
What?
1%. Seriously.
We have to talk about that.
Kansas has a 4%. T's just said it. Anybody else have a favorite team that's not Kansas? Gonzaga? Gonzaga has a good chance. Well, relatively. Gonzaga, 3% chance. Purdue, was it, Maggie? Purdue is actually the third highest chance, 7%.
I have them in my.
You have to do it. Kansas is at 4%. The model like Virginia and Villanova. The last year champion was Villanova, and they had a 9% chance of winning. So anyway, that's what the model says. Back to the real world. Back to the boring stuff. Let me quickly grab GLHT example here real quick. Nope, not there. You'd think I know how to get this quicker. There it is. Okay. You notice when I had you form the matrix before, it looked like this. It said matrix, and then it had the C function in it and a 1. What that's doing, if I go unpack this for you in R, it creates a column, a row vector. It has 1 row and 4 columns to it. But what it creates it from is this concatenate feature, right? So if I just use the C function, R is storing this as what it calls an atomic vector. You can't do matrix algebra on it. But once you put it in that matrix function, and the 1 after the comma says I want 1 row to it, it makes it the same information, just stored a little bit differently in R, where each row has a position and each column has a position. And now you can use matrix algebra for it. And the reason for that is GLHT wants you to have a matrix that comes in rather than the other way around. So it's a subtle distinction, but this is the thing that screwed me up almost the most in R. If you want to do things with matrices, you have to make sure they're officially a matrix in R, even though you probably would think it should be a matrix already. Sometimes you have to go out of your way to ensure that it is. So let's go a little bit further. My X matrix is here. Here is X. You'll note it's one of the things when R displays the matrix for you in the terminal or in the console window right here, you'll note it lists for me in brackets blank comma 1, blank comma 2. That's the syntax you give if you want to give that specific column in R, right? So for instance, X blank comma 1 gives us only the first column. But again, we have to wrap that in the matrix function because you see how it output this? You don't see column headers here. You only see this number over on the side. That's an atomic vector. It took it out from being a matrix and made it into a vector. Can't do matrix algebra for it. But here is the column vector of the first column. All right, it's 1,000 rows and 1 column. And similarly, if you wanted just one of the rows of X, you would do the same thing, but you'd put the row number in the first spot, a comma, and nothing beyond it, and you would have that row. So this code right here gives us the very first row of X. Now you'll note this, although it just put it in a column vector. If I did this, it would make me have a row vector. So I'm going to save each of those column vectors as matrices for later. You can also point to an element of a matrix by telling it which row and which column you want. So X102 gives us score 470. And if we just show you what that is, if we go to row 10, column 2, that's the 10th person's observation on whatever the second column is. SAT math, I think it is. Okay? So all the things that we saw before you can reinforce with the example here. And actually, to transpose a matrix, you can take the T, put the matrix in the T function. T, nice lowercase t, nice and simple. So if X was this 1,000 by 2 matrix. By the way, to find out the size of a matrix, the function is dim. It tells you rows and columns. Dim for dimension. So X is 1,000 by 2. And the transpose of x, x transpose, how many rows should it have? 2 by 1,000. Right? So the first number is always the rows, and the second number is going to be the columns. Right? And so x transpose looks like this, although it doesn't print it as well because it's trying to put all the first row in first and the second row second. I bet I could doing that. There it is. Oh, no, there it is. It says very wide, right? Okay. Here's us playing with vectors. We have A and B here. We have the length. We can do vector addition. I showed you all this in the slides. It's not that important, not that great. But now let's go back to the slides to the parts that are great. And when this becomes phenomenal, I'll switch back to R. I know what you're thinking, right? Don't bother switching, right? Hang in there. I promise there's meaning to all this, all right? Okay, so we talked before about a linear combination, right? Y equals A1x plus A1x, A1, the scalar A1 times the in this case, column vector x1, plus A2, the scalar, times the column vector x2, and so forth. We set that up, and why I set that up is because we can also describe something called a linear dependency in data. Right? So for instance, if you had a set of vectors where you form them such that you make this linear combination, and the result is not 0, right? So the result is some number, and you plugged in the set of scalars that are all not equal to 0 either. Right? Pardon me. I screwed that up. The vectors are linear dependent if the sum of the linear dependency is 0 when all those A's are not 0. What do I mean by that? Let's try this. Have you ever been in a lab where you're like, well, I collected SAT verbal and collected SAT math or something like that, but you know, I'm worried about the SAT total. Let's go and put in our data the SAT total as well, right? So you make SAT total is a linear combination. It's 1 times SAT verbal plus 1 times SAT math. Sounds good? Let's all put those in as predictors in college success. SAT math, SAT verbal, SAT total. Ever done that before in a lab? I have this request pop up from time to time. Didn't know if you've ever been exposed to that. Turns out, to do that would be very bad. Like what is the guy from Ghostbusters? It's like bad. Crossing the stream's bad, right? Because if we take 1 times if we put all these in the same data set, SAT verbal plus 1 times SAT math plus -1 times SAT total gives us a 0. These vectors are called linear dependency. It means that the information in some small set of it, basically there's redundant information in that set of 3 vectors. And that causes the linear dependency is the source of multicollinearity in analysis. You've heard that word before, right? And actually people talk about, oh, multicollinearity. It's usually like, that crappy reviewer that you get on the paper that has nothing else bad to say, they usually pull that one out. But what about multicollinearity? You ever heard that? Have you seen that? Maybe when you submit papers, you will. Anyone know this paper? No. No. Ahmed, maybe. You know that bad. Thank you. At least you're giving me hope that I'm one person. Multicollinearity is a linear dependency. What happens in multicollinearity is, I mentioned to you before, I'm going to give you technical information here, X transpose X inverse X transpose Y is the formula we use to do the least squares. And if you put SAT verbal, SAT math, and SAT total into X, you cannot find the inverse. It blows up. Because you cannot find the inverse of a set of vectors or a matrix that's linearly dependent. Not a traditional inverse. There are things called generalized inverses, but not the way. Yeah.
It's also related to, in terms of linear regression, when two
Yes, but it's not the level of bad that people make it out to be. So you're going to often have correlated variables. It's fine. But where it becomes problematic is when you can't take an inverse.
Can I just ask
Yeah.
expert,
Mm-hmm.
what do you think, how high the correlation is too high in terms of, does it depend on?
I don't think there is too high unless the computer won't give you reliable numbers on the output. So that's the point I want to make. Collinearity or multicollinearity, whichever way you want to call it, I've heard it called both, is only a problem when you can't take an inverse of the matrix. And when that happens, what happens to your model is typically the standard errors for each of your betas become astronomically large. Like they start to look like infinity. I mean, like if your beta slope is like 20, the standard error of it is like 2 million. Like if it's taking up so much space in the output that it almost goes into different columns, there's usually a problem with a linear dependency, multicollinearity. But absent of that, there's no numerical reason why they can't be in the model at all. Well, the E notation, yeah, that may show up in the standard error when it's not over in the betas themselves. But it's really it's not a numeric problem. Now the other problem is when you put variables are highly correlated in, they're likely not going to do the same thing. I mean, they're doing the same thing, so you're going to get redundant effects. You may not want them in just from a conceptual point of view, but I don't know that starts getting into territory I don't want to get into. From the part where the reviewers I've seen complain about it, it's not a problem. So that's me. That's linear dependency. Other questions? All right, we're going to add some more. We're going to do our first bit of multiplication here. We talk about the vector geometry. Remember that picture of the vectors on a graph? One of the things that is an important piece of geometry is something called the dot product or the inner product of those vectors. This is where it's denoted often A dot B right here. And the way we form it is taking a product of each of the product of each of the elements of the vectors and adding them together. When we get to formal matrix multiplication, it's actually going to look like this, A transpose B, but we're not there yet. So we take, so let me give you an example. From our example before, our vector A was 1, 2, that was A, and B was 2, 3, I believe. So here, if we take 1 times 2, this pair right here, and we take 2 times 3, that's right here, and then we add them together, we get an 8. That's what that happens to be. Do the same thing with our data, we get very big numbers. But why this becomes important is because the dot product is related to the angle, right? The degree of angular, the kind of the angular distance between the two vectors. If we were to go back to that graph I had before of A and B right here, this angle between them right in there, right there, is related to the dot product. And there's a relevance to all of that because that angle between them is very directly related to correlation. Two vectors that are highly correlated have a very small angle between them. Two vectors that have zero correlation are perpendicular to each other. 90-degree angle between them. Right? So, getting into this, here's the angle between vectors. That's an inverse cosine. That's a dot product up there, and each of these are the length of A, the length of B. Okay. So for our example, the angle between the two vectors is 0.12. The angle between our vectors and our data is 0.105. And believe it or not, if you take your data and you mean center it, right? Again, you have to mean center it first. So you take those vectors and center them by taking the mean out of it. Then the correlation between those column vectors that are mean centered is given by the cosine of the angle between them. What does that mean? I don't know. It gives you a nice visual representation. So if you think about it, as those vectors get real close to being right on top of each other, the correlation is going up and up and up. If you think of a vector that's perfectly correlated with another, what it's doing is effectively going from 0 to the same part of the line somewhere. Right? It may be too far or too little, but it's going in the same direction. The angle would be effectively 0. As that angle is 0, gets close to 0, the correlation goes to 1. That's really what we're talking about. Okay.
So in this example here at the bottom, that would be highly correlated.
That's right, very highly correlated.
Is that actual degree?
This would be in, I believe, radians, if I'm not mistaken. So, and cosine is, so that, my God, my trigonometry is terrible. But there's, someone want to help me? What's the range of the cosine goes, if you talk about the Cartesian coordinate system, if we talk about the number of degrees, we could also talk about that in terms of radians. So effectively a circle around there would be 2 pi in that. What you have here is theta would be in radians. You can convert it to a degree measure, but I can't remember any of that stuff at the moment now. I'm sorry. So all of a sudden, I'm sorry. You haven't looked like you know this, Jacinta, or Kevin. Jacinta, do you help?
I sort of remember it. I taught it.
Okay, so this is it. This is it for me too. I'm like, yeah, I sort of remember that. Yeah. You can tell it's not in. Yeah. Minus pi. So that's right. The range of cosine goes from minus pi to pi. Right? Is that? Thank you. Thank you very much. And so yes, you can tell I don't focus on it much. It's more to try to give it. I should have looked this up, make myself look more knowledgeable. But you all know that I fail all the time. So there. Well, okay. So now we're getting there. We're almost done with vectors. But here's where regression starts to get interesting. We're going to talk about vector projections. What? What is a projection? So if you have a vector A here and a vector B here, a projection is like thinking of if we were to go above B and shine a light down, it's kind of be where the shadow of A falls on B. There's a formulaic number that can go to it, but the projection of vector A onto B is the orthogonal projection of A onto the straight line defined by B. So here, we can talk about this as A projection B. Why am I telling you all that? Look at that graph right there. That's regression. We're actually doing vector projection and regression, believe it or not. Right? This right here is your predicted value of Y. Right? And then you have Y going off into whatever dimensional space. So the predicted value of Y is the projection of Y right here onto the space spanned by the columns of X. Sort of this odd numeric way of looking at it. But what's interesting about that is really error happens to be the difference between the projected value of Y and Y itself. So error happens to be perpendicular to Y in that case, right? So it's unrelated to Y. And an interesting geometry to it. Anyway, does anybody think, yeah, there's like usually one or two of you come up after class. Yeah, I knew there was something like that. That was never me. All right, so what do we have here? We can do this with SAT Math and SAT Verbal right here. And we can see that this, if we took the actual values, again, we have to mean center these vectors. If we took the actual values and plugged them into the projection formula, we'd see that that number right there happened to be 0.475, and sure enough, that's the number that's associated with the slope. So there's a direct connection between geometry and what we're doing in statistics. That's where I'm going. Okay, cool. Going back to R, you can see all of that here. You can actually go through all my code and show it. One thing I wanted to note about R is to do matrix algebra in R. One of the things, the dot product I talked about before, I mentioned that we needed to take there was this A transpose B that involved in it. If I flip back to my slides. There, this thing. The dot product is given by A transpose B is what I said. R doesn't, actually R has an inner product function. I didn't use it, but I'm just going to show you the dot product version of it in R, a vector version. If I take the transpose of A, it's now a row vector. I have for B a column vector. And in R, to do a matrix multiplication, you take this the percent symbol, you put an asterisk between two percent symbols. That's what this says right here. That says don't multiply T of A and B. In fact, if I were just to take off the asterisks like this, it wouldn't be able to do it. Right? It can't do that. It says non-conformable arrays. I'll show you why in just a moment. But if I do it this way, it gives me the dot product I'm looking for. Right? So to do matrix algebra in R, it's already built in. It's with percentages and so forth. So you can see all of that. Okay, questions? Everybody looks really bored. Boring? Hang in there. It's getting better. It's going to get better. As soon as we get to data, it will be much better. You're going to be like, again, I'm going to autograph the slide. Like, come up to me and be like, hey, can I have you sign your slides? No. That's such amazing. Have you ever done that to a professor before? I dare you to do this to one of your professors in some other class. Like, that was the most amazing lecture. Could you sign your slides for me? See what they do. Like, if they would just like. Yes. R, yes.
So how would you interpret when you run a line with dot vectors and you got one?
Where is this right here?
Yeah. Yeah.
So this describes, the dot product describes sort of the, it turns out to be the, it's involved in the angle between the two vectors. It's actually involved also in the projection between the two vectors, right? And so because of that, that dot product, the bigger that happens to be, the bigger the angle between the two vectors happens to be. I think that's the only way I can describe it as. It's not really meaningful, but I think you could relate it to, I mean, meaningful for us, it's meaningful for quite a few things in other parts of science and engineering, but for us in statistics, it quickly loses its meaning. We typically talk about, our version of angle between vectors is correlation, right? Correlation is highly related to what the dot product is giving you, and that's because really the dot product is a part of that angle between the vectors. That's all. So it's not really doing it. I'm only bringing this up to try to provide a little bit of visualization with the numbers and the vectors rather than just straight discussion of it. But that's the closest I can get to you. So does that help? Other questions? Okay. Back to, uh-oh. Yeah. Let's try this again. Let's go to a slideshow. Go. All right, here we go. Matrix algebra. Make this a little bigger. Maybe. Okay. So a matrix, once we talk about vectors, a matrix is a collection of those vectors, right? We had column vectors before, we can keep working with those. It's a box of vectors, right? So the matrix operations that we typically do are each of those vector operations. We talked about addition, we talked about the dot product. Those both show up in matrix algebra, but it just shows up for each of the columns that show up in a matrix. Right? So instead of just talking about addition of two columns, you're going to add all of the columns in a matrix. So we're going to define a few things in our version of matrix algebra to make things work. I am trying to make this mirror what I remember in algebra. That doesn't necessarily mean it's your algebraic experience. But what am I going to define? I'm going to define an identity matrix, which is going to be like the concept of the number 1 in algebra. The identity, what does 1 do? Anything multiplied by 1 is itself. What does the identity matrix do? Anything multiplied by the identity matrix is itself. Now it's a matrix addition, and so it's sort of a little bit more complicated than one, but the concept is still the same. The same thing with the zero vector. What does zero do in numbers, scalar numbers that you know before? Everything goes to zero. Anything multiplying zero becomes zero. The zero vector will do the same thing. Any matrix multiplying the zero vector becomes zero. And then there is something called the ones vector. The ones vector does not have a numeric analog that I'm used to, as distinctly as 1 being the identity and 0 being kind of null. But what the ones vector actually enables us to do is a bunch of addition quickly. Right? So it kind of takes the place of wherever we had like sigma x. We're going to find that that's really easy to do with a matrix of x and a ones vector. It'll quickly add numbers for us. And so just hang on to that for a second. I'm also going to show you the basic operations of addition, subtraction, multiplication, and I put it into quotes as division. It's not really division, but it's similar. This is where the matrix inverse shows up. Inverse. So let's talk about matrix addition and subtraction. The rules for each of these, by the way, for each of these operations, they are defined on only certain matrices. And generally speaking, they are defined on matrices of given sizes, very similar sizes. So not all matrices can be added together. And the reason for that is the box has to be the same size. Right, so when we get to matrix addition and subtraction, to add two matrices together, they both have to have the same number of rows and the same number of columns to the matrix on either side. Right? So here's A, here's B. There are 4 rows in A. There are 2 columns in B. So therefore, to add anything to A, we need anything that we add to A has to be in the form of a 4 by 2 matrix, and sure enough, B is 4 by 2. So we can take A, we can add it to B because it's the same size itself. That's right. So if we did this, we take a look at, go back to our example. That's a good point. X, the size of X is 1. Oh my goodness, 1,000 by 2, right? And we also know that the size of the transpose of X is 2 by 1,000. So if I wanted to take X and add it to X, I would get a number. But if I added X to the transpose of X, it would tell me non-conformable arrays, right? So this, when I first learned matrix algebra, this weirded me out. How can you not add two things? It's one of those things where you just have to be comfortable with it. Those two things are on like different, like length, different like, they're different dialects of the same language. They're not able to be associated together, right? And so, like adding apples and oranges or something, comparing apples and oranges. I think that's another way. I'm trying to find an analogy that makes it work for this. So not all matrices can be added together, but that's okay. So think about when in our data, that data frame, if we took the data out of it, we have the same number of columns, we have the same number of rows. Right? We have the same number of observations, right? We may have different numbers of variables, but we can build matrices of the same shape. That's why data frames and data sets tend to be very regularized with matrices. They're very rectangular. There's typically observations are in the rows, variables are in the columns, and that's where we end up seeing things, right? The other thing I'll note, to do subtraction, it's the same thing. It's an element, so addition is an element by element addition. A plus B, the matrices A plus B, result in the very first element of A and the first element of B get added together to become the first element of the new matrix. Right, so it's just element by element, we add these things together and we get our brand new matrix. Seems pretty straightforward. Seems how you'd want it to work. It's how it worked with if these were each columns, that's how it worked with the column vectors we just saw. Same thing with subtraction. Whoa, back up. Subtraction, we have, if A minus B would be the first element of A minus the first element of B, or element by element subtraction. In the case of addition, the order of the matrices does not matter, right? A plus B is equal to B plus A. In subtraction, that's not the case. A minus B is not equal to B minus A, and that's because subtraction does not necessarily, it's not whatever that property is, and I'm forgetting it now. Anyway. Okay? Addition, subtraction, pretty straightforward. Here's where things get really, really crazy. Multiplication sucks. The reason for multiplication being more complicated is that what has to happen is your matrices have to align in a very new, interesting way. So maybe we want to multiply A and B together. A has little r rows and little c columns. B has to have the same number of columns that A has in rows. Right? So the rows of A, the columns of A have to match the rows of B. B has to have the same number of rows that A has in columns. If these don't match, forget it. Yeah. The matrix B has to have the same number of rows that A has for columns. Otherwise, things don't match. And one way we can quickly show this is we have our X matrix. If I do a matrix product of X, remember, X has 1,000 rows and 2 columns. To multiply X by any other matrix, and this second matrix is sometimes called the post-multiplying matrix, that other matrix has to have the same number of columns, of rows, pardon me, that X has in columns. So the other matrix would have to have 2 rows to make that work. But we know that X is 1,000 rows by 2 columns, so multiplying X by itself would give us non-conformable arguments. We can't do it. Right? So that's part of the reason for it, part of what happens. So when we do have matrices that work together, so for instance, how many rows does the transpose of X have? 2 rows. How many columns does just X have? 2 columns, right? So the pre-multiplying matrix now has 2 columns. The post-multiplying matrix has 2 rows. Sure enough, we can do this. We can multiply the 2 together, and we get a result. Whoa, man. Oh, back up there. The size of the result, though, is going to be equal to the number of rows of the pre-multiplying matrix and the number of columns of the post-multiplying matrix. All right, so flipping back to the slides, this new matrix C that's formed by A times B has the rows of A and the columns of B. Kind of an odd thing to see, right? So, similarly, we saw X was 1,000 by 2. We saw X transpose was 2 by 1,000. So the size of the result would have the rows of X as rows, 1,000, and the columns of transpose of X as columns. So it would be a 1,000 by 1,000 matrix. It's a big matrix, really quickly. What do you think happens if we flipped it? What if we said, we're going to take the transpose of X and multiply it by X? Can we multiply it first? How many columns does the transpose of X have? 1,000, right? So as X had 1,000 rows and 2 columns, the transpose flips those 2. So we have 2 rows and 1,000 columns, really wide. So this is a 2 by 1,000 matrix, and we're going to try to multiply it by a 1,000 by 2 matrix. First question, can we multiply them? Remember, the rule for multiplication is the rows of the second matrix have to be equal to the columns of the first. You might be able to. See, now you can see the part of why the transpose becomes useful, is it sort of says, hey, you can't multiply these directly. Maybe I could just reconfigure them like a puzzle. And okay, it's a little bit more complicated. There's usually a reason for it, but yes. But this right here should be able to work because we have a 2 by 1,000 matrix and a 1,000 by 2. So it should work. Ta-da! It worked. What is the size of this new matrix? 2 rows, 2 columns, 2 by 2. Right? So it's the number of rows of the pre-multiplying matrix and the number of columns of the post-multiplying matrix. So that's how we get that. So, as you'll note, with this, when I took x and I multiplied it by the transpose of x, I got a matrix that was size 1,000 by 1,000. And when I took transpose of x and I multiplied it by x, I got a matrix the size 2 by 2. So quickly what you'll see is the order of operations or the order the matrices appear in multiplication, therefore, matters. Right? X times the transpose of x does not give you the same thing as the transpose of x times x does. Right? Or in this case, a times b does not give you what b times a happens to be. So that's one of the weird things about matrix algebra. This like freaked me out for weeks when I started in that class. Like, what? Why? But that's just how the boxes have to work. If you only can multiply one thing one way, if they have to fit into this weird form, again, we've got I'm taking x. It's a very long 2-column matrix, and multiply it by a very wide 1,000 column matrix. It's going to give you a big box at the end. It's going to be very different than the flip of those, right? So how does it get the numbers, though? Whoa, back up, Templin. For each of the rows of x, it does the dot product with them, with the columns. Sorry, each of the rows of the pre-multiplying matrix is like the dot product with the columns of the post-multiplying matrix. So, what am I saying? Take a look right here. Row 1 of A is A11 and A12. Column 1 of B is B11 and B21. And so that dot product that we saw before, if these were both column vectors, was element by element multiplication and then summing together, right? So the new result would be A11, B11, the first element here, the first element there, multiplied, plus the second element here times the second element there, A12, B21. And sure enough, that now becomes the very first element of the post-multiplying matrix. So what is that like? It's the way I like to conceptualize it is for every row and column pair, every permutation you can do the dot product and fill up this big matrix here. Now again, you don't have to do any of this, the computer does it for you. Just recognize this kind of what we did with those vectors when we multiplied them together is happening here, but it's happening for every possible permutation of row and column for the pre and the post matrix, right? So here, the second row of A times the first row of B results in the numbers that show up here in the second row and the first column of the post-multiplying matrix. Right? A21 times B11 plus A22 times B21. And so on and so on and so on. Right? So again, A was a size 4 by 2 matrix, B was a size 2 by 3, so this new resulting matrix will be, first of all, they can multiply because the columns of A match with the rows of B, and this resulting matrix gives us something that is a size 4 by 3. Silence. How about a break? Think about that, or better yet, give me 2 minutes. Let me describe why for data real quick. Don't want to leave you on a cliffhanger. In our data, one of the most common forms of multiplication that we find is that last one I showed you in R. X transpose X happens all the time. Why is that the case? because it gives us a matrix that looks like this. The diagonal elements of this new matrix, first of all, it's a square and symmetric matrix, right? That means the numbers in the off diagonal match numbers in the lower triangle match the numbers in the upper triangle. They're reflected. The diagonal elements of x transpose x are the sum of each variable squared. Where have you seen the sum of each variable squared before? You remember your stat classes that talked about like standard deviation? This is like the analog, the multivariate analog of what we're doing here is getting toward a standard deviation. It's not quite there yet because we didn't mean center and so forth, but just think of it that way, right? It's also the length of that, or it's related to the length, it's the squared length of that vector in Euclidean distance, right? The off-diagonal elements now is the sum of the product of the first and second variable, of each pair of variables. The sum of, sometimes we call it the sum of cross products. Often we call these the sum of squares. In the off-diagonal, we often call the sum of cross products. And these things have very meaningful terms when it came to correlation. Right? To calculate a correlation, you actually had to find this sum if you're doing the hand calculation formula. And sure enough, that's where it shows up. So oftentimes, we can quickly talk about sums of squares or things that show up in variances by just taking x transpose x rather than dealing with the sum of squared terms. And I'll show you more of that as we go forward coming up. So how about we take a break for 10 minutes? About 35 after on that clock, and that's when we'll start again, okay? All right, thank you.